we are going to discuss the concept of delay and then begin our study of two-port networks. Two-port networks will consume a bit of time because this is a very important topic in network theory, having applications in all other fields. The concept of delay can be introduced like this. Suppose we have a network N and let us say it is excited by, we are not showing a voltage or current, it is excited by an input, let us say E of t, make it f of t, where f can be can be a voltage or it can also be a current, and let the output be delayed by an amount tau. Let the network N be such that the output is exactly of the same wave shape f, but it is delayed by tau. In addition, the network N may either amplify or attenuate the signal. So, we put a constant k. Now, if you find the transfer function of this network h of s, Laplace of the output to Laplace of the input, it is simply e to the minus s t, s tau, e to the minus s tau. Is that okay? All right. Which means that the frequency response of this network is k e to the minus j omega tau. In other words, the magnitude the magnitude of h is a constant, magnitude of h of j omega is a constant, and the phase phi omega is equal to minus omega tau. Okay. Tau is the delay of the network, and in the time domain description you notice that there is no element, no parameter called frequency. It is simply a function of time, it is also a function of time. Okay. Tau is a constant independent of any other parameter of the network. All right. Now, you notice that the phase under this condition is minus omega tau, and therefore, phase is related linearly to frequency, and therefore, this is a situation of a linear phase. Okay. I could have phi omega equal to minus omega tau plus another constant, some r times pi, for example. Even then the phase is linear, it obeys a linear relationship with the frequency. Now, the impact or the importance of the linear phase is shall be obvious in a few minutes, but look at this, phi omega equals to minus omega tau and tau, if phi omega is given, tau can be extracted in either of two ways. I can divide phi omega by omega, take a negative sign, or I can differentiate phi omega with respect to omega and take the negative sign. Tau, in either case, tau is equal to the same. However, this is a situation at frequency omega and when tau is a constant. There are circuits, there are networks in which tau is a function of frequency. The tau is a function of frequency, and if tau is a function of frequency, tau of omega, then obviously these two shall be different. These two are equal only if the phase is linearly related to omega with the constant equal to 0. You see, if phi omega was minus omega tau plus another constant, then phi omega by omega would not be equal to d phi omega by d omega. All right. And therefore, this is a very special situation in which the phase is linearly related to frequency with the phase at 0 frequency equal to 0. That is the straight line passing through the origin. In general, this is not so. In general, phi omega by omega in general is not equal to d phi omega by d omega, and in general this quantity with a negative sign is called the phase delay at the frequency omega, It is called the phase delay at the frequency omega, and this is called the group delay at the frequency omega. You shall encounter these two terms once again in electromagnetic theory, EM theory. Why a negative sign? Because delay tau has to be positive. Okay, tau has to be positive. You cannot advance a frequency. You don't. Pardon me? On the other side also, yes. Thank you. Oh, that was the mistake. Okay. So these are the general definitions of phase delay and group delay, and the quantity that we shall be concerned in network theory would be group delay rather than phase delay, and therefore we formally define the group delay or the delay. Simply we shall call it delay, and if we say delay it shall mean group delay. We define tau, the group delay or delay, and in general it is a function of omega. It is defined as the negative gradient of phase minus d phi omega d omega. All right. This is the definition of delay. Now the significance. Why do we? Well, the physical significance I have already told you, that an ideal transmission system which does not distort the waveform, an ideal transmission system, for example a communication channel, the telephone line for example, if someone speaks here, it should be heard on the other end of the line exactly as it is spoken. Okay, and then the group delay, the delay is important. There is a delay. As soon as I speak, the speech does not reach the other end of the line. There is a delay. So delay is a necessary evil of any system. Okay, what we want is, let it be delayed. Let it also be attenuated or amplified. If it is attenuated, we can put a repeater in the line somewhere. Repeater is an amplifier. Okay, a repeater to lift this signal so that it can be heard at the other side. But what we don't want is a distortion in delay. That is, we don't want tau to be a function of frequency. If it does happen, then as you know, any function f of t, a speech signal for example, consists of many frequencies, right from 16 hertz to 16 kilohertz. And if these frequencies are together at the sending end, when I speak, these frequencies are together. Now if these frequencies arrive at different times at the receiving end, obviously the speech would be distorted, and this is called delay distortion. And to avoid delay distortion, if there is to be no delay distortion, obviously the group delay function or tau omega should be a constant, and the condition for tau omega to be a constant is that the channel should be linear phase. The channel should be linear phase. You see, if the differential coefficient is taken, obviously in linear phase we can allow a constant, let us say c. We can allow a constant c. Okay, and c is usually pi by 2. If at all there is a constant, it is equal to pi by 2. Is the point clear? All right. So this is the importance of linear phase. Oh, that is because of a constant phase shift pi by 2, that you will see later. But the point that I want to illustrate to you, that the delay is a network parameter, a network performance parameter. It is not a parameter of the network, it is a performance characteristic of the network, and ideally we would need delay to be linearly related to frequency, then there shall be no delay distortion. You can easily verify that any of these networks, simple networks, for example RNC, okay, RNC, the low pass filter, what is the phase? Phi omega is equal to, well, what is the transfer function of this? SCR plus 1. So if you put S equal to j omega, this is the input and this is the output. So phi omega is minus tan inverse omega CR, and therefore tau omega is negative gradient of the phase. So it would be 1 by 1 plus omega CR whole squared. Is that okay? Is that okay? into CR, alright. Is it okay now? The negative sign is taken care of by the definition of tau, and you notice CR has the, if CR was not there, what would have happened? If CR was not there, then the equation would have been dimensionally wrong, because omega CR is dimensionless. It is adding to 1. You cannot add horses to donkeys. Okay? You can only add voltage to voltage, current to current, dimensionless quantity to a dimensionless quantity. This is perfectly alright, but tau omega has the dimension of time, so you must have CR, the time constant. Now it makes dimensionally correct. Okay, so, and you notice pi by 2 minus y 1 by j omega CR plus 1, phase of the numerator is 0 minus phase of the denominator is tan inverse omega CR. So this is correct. Alright. Now you notice that at low frequencies, that is omega CR much less than 1, the phase, the delay is indeed a constant. Isn't that right? And within the 3 dB frequency, what is the 3 dB frequency? Omega is equal to 1 by CR. This is the 3 dB frequency, half power frequency, and within the 3 dB frequency the delay remains to within a factor of 50% of its DC value. Alright. The half delay bandwidth of this circuit is 1 by CR. Half delay, not 3 dB. 3 dB is in magnitude. It is not 1 by root 2, it is half. It is convenient to specify it that way, because at omega equal to CR, you notice that tau omega is exactly half of the DC value. But even then there is delay distortion, isn't that right? Delay distortion will be absent only when omega CR is much less than 1, so that the delay remains a constant. Therefore delay distortion is a fact of life and one tries to avoid it. Now let us see how delay is related to poles and zeros. In general, as you know, h of s, the transfer function, can be written as continued product s minus, let us say, zi over I divided by continued product s minus pj over j, and there will be some constant k. Zi's and pj's, they can be real, they can be complex. Real is a special case of complex, correct? Real pole or real zero is a special case of a complex zero or complex pole in which the imaginary part is 0, and therefore it suffices to consider complex poles and zeros. The real poles and zeros are special cases. So let us say Zi equal to sigma I plus minus j omega I. Alright. Then you notice that the angle, the phase of this shall be phi omega shall be, this is not Zi star, okay, because we are considering real networks. If there is a complex pole, its conjugate must also occur, and phi omega you can easily see that it would be of the form of angle of the numerator. K does not contribute to phi. Angle of the numerator, which will be tan inverse omega plus minus omega I divided by sigma I. Okay, there will be a plus term, there will also be a minus term over I. We are taking pairs here, it being implied that if there is a real pole, if there is a real zero, I beg your pardon, if there is a real zero, then there will be only one term, okay, that you can take care, minus summation over j tan inverse omega plus minus omega j divided by sigma j. This is the phase of the total system, and tau omega you can now find out by taking minus d phi d omega. Okay. Why a constant here?
It's tan inverse omega plus omega.
How is it so? You see, j omega minus sigma I plus minus j omega I. alright, and therefore I think this should come, let us put this as minus sigma I, then it will be j omega plus sigma I plus minus omega I. So, the imaginary part is omega plus minus omega I, real part is sigma I. Okay. But obviously sigma i's, what is the restriction on sigma I? It should be no, zeros are not restricted. It is, the restriction is on the poles. Okay. Whatever the case may be, this will contribute to a delay which will be negative. If the phase is positive, minus d phi d omega will be negative, and this will contribute a delay tau 2 which will be positive, and the overall delay must be positive. Okay. Overall delay must be positive. If the function will be such that the overall delay is positive. If the overall delay is negative, then obviously the system is not realizable. Even if it is realizable, delay loses its meaning. Delay is a matter of definition, isn't it? So, delay loses its meaning. Anyway, let us look at one particular complex pole and see what happens. Let us look at a pole due to, let us say, minus sigma 0 plus minus j omega 0, let us say. Let us say there is a pole P0 which is this, and therefore the term S minus P0 which with S equal to j omega becomes j omega minus j omega plus sigma 0 minus plus j omega 0. Okay. The pole factor would be S minus P0. I am considering a particular pole. Well, let us take the plus sign. Let us take the plus sign here. One particular pole. Its complex conjugate can be treated in the same manner. If it is plus sign, then this will be minus sign. Okay. I am just taking one of the poles here, where this is minus sigma 0 and this is j omega 0. Okay. Now, due to this, the angle would be tan inverse omega minus omega 0 divided by sigma 0, and pardon me, negative. Okay. The angle contributed by this pole would be this, and if I take minus d phi d omega, the expression for the delay, let us say tau 0, the contribution to delay by the pole P0, let us call it tau 0. Tau 0 would be sigma 0 divided by sigma 0 squared plus omega minus omega 0 whole square. This is the contribution to the delay by a single complex pole. Its conjugate naturally shall contribute to omega plus omega 0. Agree?
It should be sigma 0 square in the numerator also.
It should be sigma. No, it is not. Why do you have negative sign? Because this is a pole.
When omega is 0, sir,
Then
the contribution is positive.
When omega, the contribution is positive for all values of omega, because omega minus omega 0 squared cannot be negative, and therefore the contribution is always positive. Contribution due to a pole shall always be positive. Contribution due to a 0 will be negative, but the overall, the sum of the two should be positive. Then delay has a meaning, otherwise it does not have a meaning. Okay. Now look at this. I emphasize this is the contribution to delay. Let me write down. Contribution to delay by a pole at minus sigma 0 plus j omega 0. You have to sum up all such terms for all the poles. Let me rewrite this expression. Tau 0 equal to sigma 0 divided by sigma 0 squared plus omega minus omega 0 squared. You notice several things, that number 1, the maximum value of tau 0. Tau 0 maximum obviously occurs when the denominator is a minimum, and the denominator is a minimum, the variable is omega, so the minimum value of this is 0. Agreed? And therefore tau 0 maximum is 1 by omega 0. Alright. Second, delay is equal to half of this maximum delay, that is 1 over 2 sigma 0, when omega minus omega 0 squared is equal to sigma 0 squared, which means that omega is equal to sigma 0 plus minus omega 0, or is it the other way around? Okay, that is
Plus.
omega 0 plus minus sigma 0. All right. Now obviously these are the half delay points, exactly like half power points. The two frequencies omega 0 plus minus sigma 0 are the half delay points, and if we go to the pole 0 sketch, omega 0 is somewhere here and this is sigma 0 minus sigma 0. Now if with omega 0 as the center and sigma 0 as the radius, no, omega 0 as the center and sigma 0 as the radius, correct. That means this distance, if we draw a circle, let us do that. If we draw a circle, where do they intersect? This will be omega 0 plus sigma 0 and this would be omega 0 minus sigma 0. So you can find geometrically the two half delay points as this. Agreed? The two half delay points were omega 0 plus minus sigma 0, and you notice that if both of them have to exist, then omega 0 must be greater than sigma 0. Is that clear? Due to a single pole, you see, otherwise it will go negative. That means there are not two positive frequencies at which the delay is half of the maximum delay. Okay, and the maximum delay occurs here at omega equal to 0, the DC value. You also notice that the half delay bandwidth is simply twice sigma 0. Okay. This is the third point to notice, and the fourth point to notice is that half delay bandwidth multiplied by maximum delay is equal to 2, which is a kind of an uncertainty relationship. Isn't that right? That is, if you want a half delay, a large bandwidth, then your delay has to be small. Agree? If you want a large delay, then it has to be a narrow bandwidth. The product is a constant, and this kind of an uncertainty relationship you shall continue to get in electronics, in communication, and of course in physics, Heisenberg's uncertainty principle about that momentum and position measurement. Now the this reflects very well in network theory, that the half delay bandwidth and the maximum delay, the product is a constant. You cannot increase both, or you cannot decrease both. All right. If one is increased, the other shall decrease. If the other increases, the first one shall decrease. Okay. The final observation that we make at this point on delay is that if we have an all pass transfer function, what is the characteristic of an all pass transfer function? If the denominator is d of s, the numerator would be no. The numerator polynomial. I have taken k out, so the polynomials. Pardon me.
ds itself.
No. If it is ds. Pardon me.
Then the numerator and denominator will cancel out and you have a constant.
The same
No, that should be for s equal to j omega. Magnitude should be the same. Magnitude of the numerator polynomial and the denominator polynomial should be the same. But I have already talked about all pass filters. Poles and zeros are mirror images of each other. So if d of s describes the poles then d of minus s shall describe the zeros. Isn't that clear? Let us take the first order. We have a pole here, let us say at minus a. So, my pole factor is s plus a. The numerator, that is the 0 must be here, which contributes to a factor of s minus a or minus s plus a, and then you can adjust your constant. Okay, adjust your constant such that it fits the given network, and therefore this is of the form, if the denominator polynomial is d of s, the numerator polynomial must be d of minus s. It is the same story with regard to second order. Let us say s squared plus twice zeta omega n s plus omega n squared. If this is the denominator and it is an all pass function, then simply change s to minus s. So, this does not change, but this changes, minus twice zeta omega n s plus omega n squared. Then you adjust your k. This is the second order all pass filter, and you notice that the poles and zeros shall be exactly mirror images. You go minus zeta omega n and you put the poles here, then because of the change in sign, all that changes is it becomes plus zeta omega n and the zeros must be here. Okay. You remember this, that the all pass function is described by a constant multiplied by two polynomials multiplied by a rational function, one of which is the mirror image of the other. Okay. The polynomials are also called mirror image polynomials. The two polynomials are said to be related through a mirror image, which refers obviously to the roots of the polynomials. Okay. D of s roots are the poles, d of minus s roots are the zeros, and they are in mirror image with respect to each other. Now, if that is so, what can you say about the angle of d of minus s and the angle of d of s? The same, but it is change of sign. That is right. And therefore, for an all pass network function, for an all pass function, phi omega would be equal to minus twice angle of d j omega. Is that clear? Minus twice angle of d j omega. Minus angle of d j omega is contributed by the denominator, and the same shall be contributed by the numerator. Okay. So, if that is so, then for an all pass filter, finding out delay should be simpler, because all you have to do is to find the angle of one of the polynomials, multiply by minus 2, that gives you the delay. Okay. Now, why am I discussing all pass in so much of details? Because that is the only use of all pass functions. All pass functions cannot discriminate in magnitude, it can only discriminate in frequency, in phase. Okay. So, phi omega, now the tau omega that is given by an all pass filter, all pass function, it can be utilized to equalize channels, transmission channels. That is, you have a channel, let us say a telephone line for example, and there is a source here, there is a reception here, and there is a delay distortion. So, what you can do is, if there is delay distortion, then before you connect the receiver, you can put an all pass network here. If the delay, what I want is, my ideal is delay should be a constant. Suppose the delay suppose the delay goes like this, then you can use an all pass filter whose delay goes like this, so that the sum of the two delays is a constant. Okay. If you have two systems in cascade,
This graph is between delay and frequency.
that is right, tau versus frequency. I want ideally it to be a constant. If the channel goes like this, then I can use an all pass function whose delay goes like this, so that the sum of the two delays is a constant. Why am I taking this sum? Because in cascaded system the phases add, the magnitudes multiply. If the phases add, the delays should also add. all right, and this is the use of all pass functions. All pass functions are extremely important in communication, and the major use is delay equalization. Delay equalization, which means that introducing a all pass function or all pass network to make the overall delay in the region of interest a constant, or to make the system into a linear phase 1. In that sense, we can also say that what you are equalizing is, it can also be called phase equalization system. Phase equalization means that phase is converted to a linear function of frequency. Point clear? All right. Any question at this point?
So this relation that you mentioned, that uncertainty sort of thing.
Yes.
Is it a design constraint at all? Because it doesn't seem to be.
Is it a design constraint at all? You see, what I talked about was due to a single pole. Single pole, okay, you have to combine it with its conjugate, you have to combine it with other poles, you have to combine it with zeros, and therefore one cannot say whether the overall half delay bandwidth multiplied by overall delay is a constant or not, but for an individual pole this is the case. And you might design a network, you might design a second order network, or simply maybe a first order network. For a first order network this is obviously true, for a second order network also it is true, but it cannot be said whether it is true for the overall. But it is a kind of a universalization of a principle.
So that means if you are summing up all the phases, you cannot say this.
You cannot say this, correct.
And for
All
that,
you can say confidently is about a single pole, yes.
for that we will have to find tau max and again the half power.
Half delay, yes. Half delay bandwidth, yes. Any other question? Well, we start our discussion on a two-port networks. Yes.
Is T0 the maximum value of delay?
Is T0 the maximum? What is T0?
D0. Tau.
Not necessarily. Oh, there are, I told you the equalization. You see, obviously maximum value is not here. It goes on. It could be that the delay shows a peak. That's also possible. In fact, it did show a peak. In the single pole case that we dealt, the delay was maximum when omega was equal to omega 0. So at omega 0 it's a maximum, then it falls down. Okay. All right. Any other? We shall come back to delay later on in the course when we talk about characterization of channels or networks in terms of its rise time and delay, and we shall again meet the same uncertainty principle. Okay, this will come back a little later in the course, but after doing some of the more essential network descriptions, and one of these descriptions corresponds to concerns the two-port networks. As I have already introduced to you the terms port and terminal. Would someone tell me what is a port? A port is a combination of two terminals. That's all.
So from there we can input power or we can take out push.
Okay. So suppose a network is given in which sources are already connected and your reception points are also known. The output points are also known. Now, how do you recognize the ports? A network is already given. This recording network, for example, that we have here. It's already given. It's already working. A telephone network or a communication channel. It's given. How would you identify which two terminals form a port? The currents. That is correct. A port is a pair of terminals, unless you say that it's not complete. It is a pair of terminals such that the current entering into one terminal is exactly equal to the current leaving the other terminal. This is a port. All right. In other words, this port can be terminated in a source or a load, does not matter. But for example, if you have a network like this, these two terminals may not form a port. For forming a port, the essential condition is that the current entering one terminal must be equal to the current leaving the other terminal. And if a network has two such ports, we call it a two port. If it has only one port, then we call it a one port, and if it is more than two, we generally call it a multi port. We can use the terms 3 ports, 4 ports and so on. In fact, there are if any of you go to microwave at your later stage in the career, you will encounter 6 port networks like you encounter cars and buses on the road. Okay, 6 port network is a very common thing. Now, what we are going to study is a 2 port network. One port is simple. All you can do is connect a current generator, measure the voltage, or connect a voltage generator and measure the current. Let me recall also some of the terms that we had introduced earlier with regard to a 2 port. A 2 port may consist of 4 terminals in which none of them are interconnected to any other. So, it is a true 4 terminal network where the potentials of each terminal is independently determined, or you could have a 3 terminal network in which, yes, indeed there are 2 terminals at the top, but there is a single terminal at the bottom. That is, the 2 ports have one common terminal. This is called a 3 terminal network. Now, this common terminal or any of these terminals can be connected to ground or may not be connected to ground. A network in which a 2 port network in which any terminal is connected to ground is called a grounded network. A grounded network, unlike grounded aeroplanes, it has nothing to do with that kind of a ground. It is simply setting a reference as 0, grounded network. If a 2 port network has at least one terminal grounded, it is called an unbalanced network. Unbalanced because one of the terminals has been fixed at 0 potential. So, it is the other terminals are unbalanced with respect to this.
And then what is this grounded? How is it different from
So that means that one terminal in each port for the 2 port network should be grounded for it to be
Unbalanced.
terminal case.
Unbalanced, is it?
No sir, for this grounded, does it mean that we should fix one terminal in each port to the ground? Does that mean the common reference point is there? for both
Okay.
ports?
Okay, we will come back to this later. I understand your confusion. We will come back to this. We will not introduce the unbalanced term now. Okay, we will do it later.
So, and grounded is one of the terminal is grounded.
One of the terminals is grounded. Okay.
So, both the port or
No, one of the terminals of the 4. Suppose this is grounded, then we will call it a grounded network. Okay. All right. We will call it a grounded network. In general, these terms are popular terms. I mean, they have nothing to do with technical characterization. Technical characterization, 4 terminal, 3 terminal. This third terminal may either be connected to ground or may not be connected to ground. We do not care. All right. It may be connected to ground or may not be connected to ground. But our voltage reference will measure the terminal, this terminal voltage with respect to this, will measure this terminal voltage with respect to this. Okay.
so in the 3 terminal case, the 2 output terminal may not form a port.
The 2 output terminals have to form a port. Otherwise,
No, sir, at
it is
the
not a 2 port.
junction,
At this junction,
this and the output.
no, we take terminals to the output, we take terminal to the input, surely, and then you can connect a source here. We force this to be a terminal. The source has to recover its current. All right, we can do that. Given any 2 terminals with the network disconnected or the network not energized, we can force any 2 terminals to become a port. Is that point clear? No? Any 2 terminals to become a port. Suppose I have a complicated network like this, and let us say this terminal and this terminal, they do not form a port. but I can connect a source, then the current entering here must be the current leaving here. I can force two terminals to become ports, but that is not the issue. It is not a question of forcing ports. A network has to be meaningful. It has to serve a particular purpose. So, it is designed and the ports are well identified ahead, okay, in advance of the design. So, that is
don't even require the source. So we put anything to test the voltage or current, they form a port.
well, not necessarily, because there may be other shunt connections, okay. There may be shunt connection. For example, let us say here the current that is coming here is not necessarily going back here, is not it? So, the question of identifying a port will be a trivial question. I am sorry, I took it the other way around. Okay. Now, the point we have to bother about now is, given a 2 port, we will consider a general 2 port, that is a 4 terminal network. Truly, we call this as port 1, we call this as port 2, and we identify 4 parameters, 2 voltages and 2 currents, V1 I1 and V2 I2, and the convention is that currents go into the network exactly like the example of a 2 port that we have already dealt with, transformer. Okay. The currents go in, this is the convention. So, what we have is, and obviously if this is to be a port, then the current going out here must be I1, the current going out here must be I2. Okay. So, the quantities that we have now, terminal quantities, are 4 in number, V1 I1, V2 I2, and this is a black box. We may not know what is inside. Okay. We want a terminal description or a port description or an external description of the system. What we can do is, we can consider any 2 of these as independent variable, then the other 2 shall be dependent variables. Because there are 2 ports, you can set 2 of these as independent. You can connect, for example, a voltage generator and a current generator here. Then V1 and I2 shall be independent variables, and I1 and V2 shall be dependent variables. Okay. Or you can connect both as voltage generators, you can connect both as current generators, or a combination of voltage and current generators. Now, in how many ways can you do this? 2 quantities taken out of 4, so it is 4 C2, which is exactly 6. Therefore, there are 6 possible descriptions. Okay. And these descriptions are, if V1 and V2, these are dependent, let me make a table, dependent variables and independent variables, okay, and the description. Let me go to the next page. Dependent, independent and description. Suppose V1 and V2 are dependent variables and independent variables are I1 and I2, then the description that we get are the Z parameters, the so called impedance parameters or open circuit impedance parameters, as we shall see. If it is the other way around, that is I1, I2 are the dependent variables and V1, V2 are the independent variables, then we get what are known as the Y parameters or the short circuit admittance parameters. We shall see the meanings of this open circuit and short circuit in a few moments. On the other hand, if we have, let us say, V1 and I2, a combination, V1 and I2 expressed in terms of V2 and I1. No, I'd like to keep the orders same. So, I'll call this I1 and V2. I1 and V2, then what we get are called the hybrid parameters, H parameters, okay, hybrid parameters, and why they are called hybrid shall be clear later. I am expressing a voltage and a current in terms of a current and a voltage, okay, and naturally you see the Z parameters and Y parameters, they should be inverses of each other, okay. Similarly, I can express I1 V2, I can bring I1 V2 here and V1 I2 here. The description will be the so called G parameter, small g. Please distinguish between G and Z. Okay. And this is G. Okay. Now, another description is I have
So that is V2 I1 and I2 V1.
V2 yeah, okay, that's right. No, I do the same way, I1 V2 and V1 I2. There is a reason for putting it in this order, as we shall see later. We can have V2 I2 as dependent parameters and V1 I1 as independent parameters. Okay. Then this is called the so called transmission parameters. Transmission parameters, or also called ABCD parameters. And if I repeat this, that is V1 I1 I bring here and V2 I2 I bring here, then they are called inverse transmission parameters, or they are sometimes denoted by script ABCD. If I bring this here and this here. So these are the 6 possible cases, and the cases that we shall discuss in details are, first of all, the Z parameters, the Y parameters, the hybrid parameters and the transmission parameters. The other 2 are not very much used. All the 4 of these are extremely useful. Z and Y are useful in almost all situations. These are parameters for all seasons. Okay. The H parameter particularly is useful in dealing with electronic circuits, transistor circuits. The transmission parameters are useful in communication networks or communication systems, particularly when systems are to be cascaded one after another. We will show that the ABCD parameters multiply there. ABCD parameters multiply. Well, in addition to these 6, for a 2-port, a 2-port is a special case of a multiport in which the number of ports is equal to 2. For a multiport, there is another description which is extremely useful at very high frequencies, and these are called the scattering parameters. Scattering parameters. They are based on wave descriptions rather than voltage and current, and scattering parameters are extremely useful at microwaves. We cannot do without them, and this is an opportune moment to introduce scattering parameters to you also. Therefore, we shall discuss Z parameters. This we shall call capital S parameters. Okay. Scattering parameters are capital S. We shall introduce Z, Y, H, ABCD, and ABCD parameters for are also sometimes called the small t parameters. Transmission parameters, small t. However, we shall prefer to use ABCD rather than small t, because small t, the symbol is reserved for a well respected physical variable, namely time. Okay. We would not like to enter into that kind of a controversy. The scattering parameters we shall describe for 2-port networks. They will be particularly useful for number 1, transmission lines, which you shall study in electromagnetic theory, and in microwaves. If you happen to take a course, an elective course on microwave circuits, well, you cannot do without scattering parameters. So we shall discuss them also. To introduce the Z parameters, let me first write down the network description, or the manner in which in Z parameters, what are the independent variables? The currents I1 and I2. In other words, what we do is connect a current generator here, I1, note the arrow, I1 has to go here, and let the voltage be V1, connect a current generator here, I2, so that current enters here and the voltage is V2, this is N. what we have to do is to express V1 and V2. These are the only two other these are the only two other parameters, only two other quantities, physical quantities that you can measure, and therefore V1 and V2, these are the dependent parameters, they are expressed in terms of I1 and I2. And because we are considering a network which is linear, the voltage V1 shall be obtained by superposition, that is superposition of the effects due to two sources. First take I1, disconnect I2, find V1, then take I2, disconnect I1, find V1 and add the two. In other words, V1 shall be a linear combination of I1 and I2, and therefore the coefficients we can say K1, K2, F1, F2, whatever constants, but the usual nomenclature is Z11, Z12. These are the constants. Is the point clear how we obtain this equation? A dependent variable V1 is obtained by superposition of two effects, one due to I1, the other due to I2, and because the network is linear, they shall be superposition with constant multipliers, and these multipliers we call Z11 and Z12. Similarly, V2 is obtained by taking Z21 I1 and Z22 I2. This is how the Z parameters are defined. And if you look at this, if you look at these parameters, one can immediately see that if you want to measure Z11, for example, this constant, all you have to do is to make I2 0 and divide V1 by I1. Okay, so Z11 is V1 by I1 with I2 equal to 0. I2 equal to 0 means the second port is open circuited. I2 equal to 0 means no current flows. Source is disconnected and therefore no current flows, because this is open circuited. All right. Similarly, you can see that Z22 is V2 by I2 under the condition that I1 equal to 0. You also notice something interesting, that Z11 is a driving point impedance, isn't that right? It relates the voltage and current at the same port, and therefore it is a driving point impedance. Similarly, Z22 is also a driving point impedance. All right. On the other hand, if you look at Z12, Z12 is V1 by I2 with I1 equal to 0. Let us look at how this is done. There is a current source I2 and this is kept open, I1 is equal to 0. So, the input port is open and you measure V1. Obviously, Z12 is a transfer impedance, isn't that right? Because the effect and the cause are not at the same port, they are at different ports, and therefore, this is a transfer function having the dimension of impedance. It is a ratio of voltage to current. In a similar manner, Z21 is equal to V2 by I1 with I2 equal to 0, which means that you excite by I1 the network N and measure the voltage V2. If the network N is reciprocal, then the reciprocity theorem says that this and this are reciprocal situations, and therefore Z12 should be equal to Z21 if N is reciprocal. We are, to start with, considering only reciprocal networks. We shall take examples of non-reciprocal networks also later, but you will see that if we consider RLC elements only, L includes mutual inductance, then the networks are reciprocal, because each of these elements R, L and C are, what is the term? No? Bilateral. Each of these elements is bilateral because current flows equally well in both directions. Therefore, the total network composed of bilateral elements has to be reciprocal, and Z12 equal to Z21. In other words, we come to a very interesting phenomena, that although in theory we require 4 constants, 2 of them are identical, and therefore this is a 3 parameter description of a 2 port. 3 parameter description holds only if the network is reciprocal. All right, we will stop here.